In this video, we are going to prove the vector triple product identity, vector A cross vector B cross vector C equals vector B times dot product of vector A and C minus vector C times dot product of vector A and B by using the vector component method. This is going to be a relatively lengthier and more tedious method of proving the vector triple product identity as compared to proving it using the Levi-Civita symbol. I have already shown how to prove the vector triple product identity using the Levi-Civita symbol in another video. I will post the link for that video in the description of this video. Feel free to check it out. I think you will really appreciate the beauty and the simplicity of that proof after you have been through the proof presented in this video. Let's now begin working on proving the vector triple product. Vector A cross vector B cross vector C equals back minus cap using the component method. Let's say the cross product B cross C equals another vector D. Now, why are we doing this? We are doing this for a very good reason. This will change the vector triple product A cross B cross C into a simple two vectors cross product A cross D. Hopefully, you all already know how to evaluate a two vectors cross product, such as vector A cross vector D, using the determinant method. Let's quickly review it. First, we write the cross product in the determinant form. That looks like a 3 by 3 matrix, but it is not a matrix. The two vertical bars around the 3 cross 3 array indicate that it is a determinant. We get vector A cross D equal to the unit vector I hat times AY dz minus AZ dy plus the unit vector J hat times AZ bx minus AX bz plus the unit vector K hat times AX dy minus AY dx. Now, let's revert our attention to our original goal, and that was to evaluate the vector triple product A cross B cross C in terms of the vectors A, B, and C. So next thing we're going to do is to write down the components dx, dy, and dz in terms of the components of the vectors B and C and put them in the equation we just got for the cross product A cross D. So let's go ahead and evaluate vector D equal to B cross C using the determinant method, the same determinant method that we used to evaluate the cross product A cross D. Let's see what we get. The cross product B cross C, it equals the unit vector I hat times by cz minus bz cy plus the unit vector J hat times bz cx minus bx cz plus the unit vector K hat times bx cy minus by cx. Let's call it as equation 1. Let's now write vector D in terms of its components as dx I hat plus dy j hat plus dz k hat and call this equation as equation 2. We're going to set the coefficient of the unit vector I hat in equation 1 equal to the coefficient of the unit vector I hat in equation 2. That gives us dx equal to by cz minus bz cx. Similarly, when we equate the coefficients of the unit vectors j hat and k hat in the two equations 1 and 2, we get dy to be equal to bz cx minus bx cz and dz to be equal to bx cy minus by cx. So here we have expressed the components of the vector D, that is dx, dy, and dz, in terms of the components of the vectors B and C. And when we insert these expressions for dx, dy, and dz in our previously calculated cross product, A cross D, we get A cross D in terms of the components of the vectors A, B, and C. Let's go ahead and do it. So here for dz, we write bx cy minus by cx. Next, for dy, we put bz cx minus bx cz. And for dx, we put by cz minus bz cy. Everywhere we have a component of d, we rewrite it in terms of the components of the vectors b and c. In this next equation, we're not doing much, just rewriting the equation without the internal sets of parentheses. Okay, that was easy. In this next equation, we're not doing much. We're just rewriting the equation without the internal sets of parentheses. Okay, that is easy. Now the magic begins. We're going to group the positive terms together and the negative terms together. Now, why are we doing that? Simple answer is that we're trying to bring the right-hand side of this equation to equal back minus cap. Sounds like some weird kind of taxi service. Next, we're going to add unit vector I hat times ax, bx, cx to the very first line. But we can't just add a term. That changes the equation. So we're going to also subtract vector I hat, ax, bx, cx. So we are effectively adding 0 because I hat, ax, bx, cx minus I hat, ax, bx, cx equals 0. We will also add and subtract unit vector j hat times ays, by, cy and unit vector k hat times az, bz, cz. Next, we'll factor out bx from the unit vector I hat term, by from the unit vector j hat term, and bz from the unit vector k hat term. We're not about to stop here. We will factor out cx from the negative unit vector I hat term, cy from the negative unit vector j hat term, and cz from the negative unit vector k hat term. Hopefully, you have already seen dot product, also known as scalar product. The dot product of vector A and vector B. It is defined as ax bx plus ay by plus az bz in terms of the vector components. And similarly, the dot product of vector B and C, that is B dot C, it is equal to bx cx plus by cy plus bz cz. And the dot product of vector A and C, that is A dot C, is equal to ax cx plus ay cy plus az cz. So wherever we see ax cx plus ay cy plus az cz, let's put it equal to vector A dot vector C. And wherever we see ax bx plus ay by plus az bz, Let's set that equal to vector A dot vector B. Aha! Right-hand side is already looking close to what we want it to be, which is back minus cab. Let's go ahead and factor out A dot C from the first three terms and factor out A dot B from the last three terms. Now we have I hat bx plus j hat by plus k hat bz times A dot C minus parentheses begin I hat cx plus j hat cy plus k hat cz parentheses closed times vector A dot vector B. We know that I hat bx plus j hat by plus k hat bz equals vector B, and I hat cx plus j hat cy plus k hat cz equals vector C. And here we go. Now we have vector B times A dot C minus vector C times A dot B. I hope your brain is not too crossed by the triple cross product. Hope you enjoyed it. I sure enjoyed creating it. See you next time in another video.